One of the leading authorities in the area is Scott Weil-Petersson, who I wrote a paper with, but I still know nothing about them much, as will become apparent when I start to talk about them. So let me say a little about the geometry. So I use the following notation. I'll use S to denote a compact surface, closed surface. And this closed surface will look like that. Looks like a surface, and it's denoted by S. And on this I will put a metric, a Riemannian metric, in fact a Riemann metric. And in fact I'll put a family of these guys. So to distinguish between them, I'll call it a G subscript T. So this is going to be a family of metrics. And the genus here is greater than or equal to 2 in the picture. And so I'll assume the curvature is -1. And I can think of this as having some sort of little expansion. So I have a family of these guys. Here's one of them. Here's another one, topologically the same surface, but with a different metric. And I can think of a small perturbation of the metric in terms of some series, which might look a bit like that. So I sort of, for a metric, I'm just changing it in some nice way through some family. And I can think of this as being an expansion where I start at 0 and I change it a little. So in particular, I can think of it as being the same topological surface, and then I have some space, which isn't two-dimensional, but it's all I can draw. So this will be like the moduli space, a space of metrics. There's a reassuring sound of me breathing in the room. That's great. If it stops, it's a bad sign. And so we can think of a family of these metrics. So we start off with G0, which might be this guy, sitting on the surface. So G0. And we do a small perturbation, so it's the same topological surface, but the metric has changed a bit to G of t. So he might be somewhere out here. And what we want to do is to define the notion of some distance. And one way to do that is to think of this first term here as being like the derivative of the metric. And we'd like to define the notion of the distance, how large this derivative is. So the idea is that, so we can define the Weil-Petersson metric in terms of the size of this guy. So it's like in Riemannian geometry. You look at tangent vectors, you say how big they are, and then the distance between two different metrics or two different points in this space, we look at all possible curves from one guy to another, take the derivatives, and if we know what the norm is, the size of the derivative, we can figure out what the distance is, and that's one way to think of it. And there are various definitions of this, some of which I don't understand, but one definition is that the Weil-Petersson metric is the second derivative of the length of typical geodesics. So if you have a geodesic on here, it might not be a closed guy, but let's say it is. Here is one geodesic called gamma. He has a certain length, which might be L of gamma with respect to that particular metric, G0. And as you change the metric, there's still a geodesic there, but its length has changed. And so the length here might be L of gamma, still called gamma, but now he's got length LGT. So if we kind of average those out in some suitable way, then this gives you the second derivative of the length as t changes. This gives you the Weil-Petersson metric. So you can think of this either by averaging with respect to typical geodesics, with respect to the Liouville measure or the Haar measure, or alternatively you can average over closed geodesics in some suitable way. But rather than do either of those, let me give a simple analogy. So just to illustrate the idea. So this is a... Sorry? You can do it either way. So if we took a typical geodesic on here, then of course it wouldn't be closed because they're only a set of zero measure, in which case you'd average out along the orbits and then you would integrate over those guys. Alternatively, we're looking for a single number, so what we could do is we could look at all the geodesics up to length 1,000,000, which is a finite number, and then you average the second derivative over these guys. So either way. So the reason it's in inverted commas is so I don't want to be too specific about it. But let me be more specific in a non-example, but in a remark. So this is a remark. So a sort of a simplified setting is for graphs. Simplified setting is for graphs. So these graphs are metric graphs, so I'm going to put lengths on the sides. They're not directed graphs, they're non-directed graphs. So I'll let G denote such a thing, a graph. And I'll look at the special case that I have a graph which has a single vertex. Vertex. Here he is. And he has a bunch of edges, preferably more than 2. And I'll assume that there are k edges. And I'll draw maybe 3 of them. And I'll assume that they have lengths which are given by L1 up to Lk, all positive numbers. In this picture, k is equal to 3, of course. So here is L1, here is L2, and here is L3. Okay, so it's a graph, and it's got some lengths and other things. And this, of course, is just an element of R plus to the k, could be. Okay, and so in the case of Riemann surfaces, they have the property that their curvature is fixed, it's equal to -1. So if we fix the topology, then the area is fixed. That's a normalization for metrics on the surface. For graphs, there are other normalizations you might think of. The easiest one might be just to assume that the sum of the lengths is equal to some fixed value, but I'm not going to do that because I want to give a more dynamical normalization. And so in particular, I'll look at the space of distances metrics on here to correspond to those choices of L. Let me write this. L with the property that the sum I equals 1 up to k exponential minus L of I is equal to 1. So I don't ask that the sum of the length should be equal to 1, but I ask that the sum of minus the exponential of minus the length should be equal to 1. Why? Because it's related to some dynamical version of a definition of the Weil-Petersson metric up there. Okay, and then by the same token, that was a good question. What was it again? Symmetries, yes. Well, at the moment it's a local thing, so I don't care too much about it. Okay, and by the same token, I can look at a parameterized family in this space, and this is L0 plus, t times L of 1 plus t squared L of 2. So I can take a family of such lengths associated to this picture, And again, I can just assume that it's parameterized by something like that. I'm thinking of it just being a small perturbation of the original guy. And then, so the picture would be that we can think of any particular choice in here as being some little point sitting inside our space. And then we think of this as lying on some curve. So this would be L0 maybe. This would be LT maybe. And so we have a sort of tangent vector again. And in this particular case, we would say that the norm of what? The norm of something. The norm of the derivative of this guy. So that's the tangent vector of this guy. I won't put Weil-Petersson, I'll just put it's equal to something. And we can say this is equal to just the summation I equals 1 up to k of, in fact, Li 2 exponential minus L of I. That's a scrub I. So you look at the coefficients in the second term, and you combine them in a certain way, and that gives you a natural norm on this guy, except possibly it should be squared. It's a calculation to see that it gives you a norm. And the reason that this works is because we're assuming that these guys all lie inside M. Okay, so that's just meant to be a simple sort of... They're the best ones. Why does it only depend on L1? So you mean L upper 1? Yes. Why doesn't it depend on this term? Because these two terms are related by the fact that they lie inside this space. So the curve lies inside here. So yeah, it's a calculation, which is what I always say when I'm not going to do it. It's a calculation. Great. A good question, though. Excellent question. And the observation of Kurt McMullen was that the Weil-Petersson metric, which I haven't really defined, can be written in a similar way, except instead of looking at graphs, you look at some sort of symbolic dynamics for your geodesic flow, and then instead of a graph, you have a subshift of finite type. Instead of these lengths, you actually have some roof function, some return time function, and then pressure makes an appearance, and stuff happens, and you can recover the Weil-Petersson metric. But if you look at it in a simplified case, it corresponds to just this. So this is just a simplified thing. And the reason for saying this is that that was a remark, but there's also a sort of sub-remark, which is that once you've extracted this philosophy that you can think of these metrics in a different way, perhaps in a more dynamical way, then you can use this approach to define other things. You can use it to define a Weil-Petersson metric on higher type Muller spaces. Which is basically you take some group and you consider it somewhere in like SLDR, and then some sort of analysis which inspired by this allows you to show something or other, etc., etc., etc. And so this is a sort of thing which Bridgman, Canary, Lavery, and Sambriano do, I believe. Okay, so what do I want to talk about? Well, always was an excuse to talk about something else. Hi. You're chairman, you don't have to wait. You can just interrupt yourself. In the Weil-Petersson metric. It's true. Whether or not it's obvious, I'm not so sure. Well, in the geometric case, it is a theorem. I think it's due to Weil-Petersson. And such distinguished people as this. So it's too hard for me, basically. But it's true, I believe. Okay, so what I want to talk about is something a bit more dynamical than this even, which is I want to talk about boundary correspondences. So and how does that go? Well, having introduced, drawn a picture up there of a Riemann surface, well, one of the things I could have thought of it was instead as looking at the universal cover, which is a Poincare disk, and then quotienting out by some suitable group, which seems like a good thing to do in the context of this particular week. So this, if you like, is a more dynamical ingredient. And the way this works is I use the following notation. I'll let D2 denote the Poincare disk. So the Poincare disk looks not unlike the usual disk, x plus iy, absolute value smaller than 1, except you put some particular metric on it, and it might be the following, that the distance is really given by 4 dx squared plus dy squared over 1 minus absolute value z squared all squared, or something like that, give or take some factors, which I used to get wrong. Okay, so it's the usual definition of the Poincare disk. And of course, the thing about that is that for any Riemann surface, it has the same universal cover, which is this guy. So in particular, instead of looking at families of metrics on a given topological surface, I could think about the Poincare disk and different groups acting on it. So instead, I might like to think of my family as being some subgroup, discrete subgroup of isometries, a Fuchsian group of isometries with respect to the Poincare metric. And this is going to be, a family of subgroups. And then they correspond to the picture I just had before. So let me just draw a reassuring picture, reassuring to me, maybe not to other people, of a surface and the Poincare disk. So this is meant to be the cover for this, and then you can lift it up, and there's some group acting up here, which I will just represent by the fundamental domain of the guy up here. So here is a group acting, and it corresponds to the surface S with a particular choice of metric downstairs. Something like that. Details left for another occasion. Okay, so if we have a family of such guys, a family of surfaces, then of course what's going to happen is that the groups are going to change. So these guys are indexed by t in minus epsilon. So we could ask, if we change this family in a nice way, are they related in some way? And in fact, there is a homeomorphism between the boundaries of two of these guys. So let me draw. I think I have to clean the board soon. And in fact, there exists a homeomorphism. Let me say there exists a isomorphism, just to give me some notation. And the isomorphism is going to be just relating the original group by this group. It's the same group as a group. So this is an isomorphism. And there's also a homeomorphism on the boundary. So pi of t is going to be a map from the boundary to itself. And this will be a C alpha, in fact, for some alpha homeomorphism. And it's actually equivariant, so the picture would be the following, that we have sitting above our surface this particular guy, D2. We have the same Poincare disk over here, but maybe a different surface, like that. So this is the surface with the metric g of t. This is the surface with the metric g of 0. And what's happened is that we have different groups acting here. This is gamma 0. This group here is gamma t. And there's going to be a map called pi of t, like piety, but not piety, between the boundaries of the two guys, so between the unit circles in this particular case. And it's going to be equivariant, which means it maps orbits from one to the other. So basically, it's such that pi of t of gamma of psi, where psi is in the boundary, and gamma is in the group, presumably gamma 0. And this will be the same as what you get by taking psi, mapping it over by this homeomorphism, and then applying the corresponding element in the other group. So the picture is, here is psi, here is his image, which is pi t of psi. But if we'd applied an element of the group, which got us to here, so that would be gamma of psi, then we could have got to the same place by doing, if we map it over by pi of t, then we get pi of t gamma of psi, which is the same thing as just applying this element. It's an equivariance. It commutes, basically. Okay. And so the two metrics give rise to, so the family of metrics now gives rise to a family of homeomorphisms on the boundary. And some things are known about this family of homeomorphisms. I've already said that it's a Holder continuous, and it's a homeomorphism, so it's invertible, and there's a sort of rigidity result, which is due to Sullivan, and appears in the Bulletin of the American Mathematical Society in '82. And basically what it says is that there's two choices here. So it says that either, well, you could be in the case that this map pi of t is very nice, and very nice here means that it's a linear fractional transformation, a Mobius map, which preserves the disk. So one possibility is that for a given t, either this guy is a Mobius map, which would mean that the two metrics were isometric. And if that's not true, then the map is very bad. So it's either a very good homeomorphism or it's a very bad homeomorphism. And very bad in this case means that it isn't even absolutely continuous. And not being absolutely continuous means that your homeomorphism can misplace sets of positive measure. So in particular, it means that we can find a set which sits inside the boundary with the property that its Lebesgue measure on the boundary is equal to 0. But when you look at the image of it, it fills up the entire thing. So that is that the Lebesgue measure of, on the boundary of the disk minus the image, so that would be pi t of E is equal to 0. So two possibilities are it's either very nice or it's very bad, which means that the map just loses a whole set of full measure. Which seems kind of bad, really. Yes, I'm giving a reference, undoubtedly. I'm just giving a reference to a survey article by Sullivan, which is an excuse for me not knowing the references very well. Okay, let me play with this thing. It sounds like fun. Let me push that one up and see if I can bring any of them down. That didn't work. Okay. Can I bring that? I can certainly bring the middle one down. You want me to bring this one down? Yes, I can try. Oh, you can see I'm a bit challenged by these things, but I'll give it a go. Thank you. I aim for perfection. I don't always achieve it. Okay. So when I clean the board, you can think about something, which is there anybody here that remembers André Weil? Hands up if you met André Weil. André Weil, as in Weil-Petersson. Great. Excellent. I met him in 1988. I'm waiting till the day that nobody else puts their hand up, and I know it's time to retire. Well, that time's already passed, I'm not sure. But there is, in fact, a stronger result than this, than the one I've just stated, which is the following. And this result I found in a paper of Bishop, and Steger. And this is from 93. And what it says is basically the following. Well, in fact, this map has to be of two flavors. Either it's a linear fractional transformation, or it's even worse than one that's not absolutely continuous. So they showed that, in fact, B can be replaced by a worse condition, which I'll call B prime, which says that you can find a set E contained in the boundary with the property that not only does it have zero measure, but its Hausdorff dimension is strictly smaller than 1, and its image should have some complementary looking property. So probably that says that the Hausdorff dimension of the image, when you take it away from the disk, so that's pi t of E, this quantity should also be smaller than 1. So having Hausdorff's dimension smaller than 1 is a stronger condition than having zero measure, so this is an even worse thing than the previous statement. So let me now tell you the result of McMullen, which actually gives a proper definition of, well, a dynamical definition of the Weil-Petersson metric. So this is McMullen's result, one of many, of course, but let me just talk about one of them. So McMullen's result, and this is a definition of the Weil-Petersson metric using this boundary correspondence. And so it says the following. So given this map pi of t between two different metrics in our family, I'll let pi of t of Leb is the Lebesgue measure. So this is meant to be the push forward of Lebesgue measure, which I think means the following. I think it means that it's a measure on the unit circle, which says that pi t Lebesgue, that's the measure, when you apply it to some set B. So it's kind of helpful if this set B is contained where it's supposed to be, and also if it's Borel, then we say that its measure is probably the Lebesgue measure of the pullback of the set, something like that. So you just pull the set back and you look at its Lebesgue measure. So that's just a definition. And then the theorem of McMullen, which I'm looking for some suitable place to write it, maybe under here, is the following. Our theorem. And this is, I believe, from 2006. And it says basically that if we denote dt, so dt is meant to be the Hausdorff dimension of the measure pi t of Lebesgue. We need to know what the Hausdorff dimension of a measure is. And so the Hausdorff dimension of the measure is actually the Hausdorff dimension of the smallest set which has full measure. So it's the same as the Hausdorff dimension of the set F with the property that pi t Lebesgue of F is equal to 1, something like that. So the Hausdorff dimension of the measure, it has a family of these guys. Then in fact, if we, doesn't go any higher, then if we look at the second derivative of this family of numbers, so we have a family of maps corresponding to our family of metrics. They give us a family of boundary maps. We see what the boundary maps do to the measure. And the second derivative of this function, which turns out to have at least a second derivative, in fact it's analytic, is actually equal to the Weil-Petersson metric. So it's the size of the deformation squared, because it's a quadratic thing, up to some factor, and the factor is minus 4 over 3, 1 over the area of the surface, which of course is fixed because it's just in the same topology. So that's some definition of the Weil-Petersson metric. So this is a very nice result. if you like dynamical systems, if you like thermodynamic formalism or stuff to do with zeta functions and pressure. If you don't, it's not so nice, but it's still a result. Okay, so what I would like to do in the remaining, I'm guessing 13 minutes, would be to say something else about this. So this is one particular way to write down the Weil-Petersson metric, that is the length of this derivative in the metric and for a small family in terms of what happens to the boundary, but it involves measures. So what I would like to do is to write down something that doesn't involve measures. I'd like to write down something topological. And so maybe what I can do is push this guy up, and maybe I can pull this guy down. I think waiting for the other board to come down would be like waiting for a bus, so I will be expedient and do it this way. Okay, so the plan is I'd just like to give another variant on this, which doesn't involve having to look at the Hausdorff dimension of some measure, because today I'm measure averse. So the aim is to give a proof or a result which doesn't involve measures. So for a measure 3 definition, thermodynamic definition of this metric. Thing I didn't mention was that there's another interpretation for the Weil-Petersson metric in the work of McMullen, which is actually quite nice as well, which is that it corresponds somehow to a dynamical property for the original surface G0, and the dynamical property is related to the central limit theorem. So it's the intrinsic dynamics of the fixed surface, and the central limit theorem is about how functions behave, and the functions in that case are related to G1. So a throwaway comment is that you can actually interpret these things dynamically in terms of central limit theorems for geodesic flows, which a lot of people who work in the area like to play around with. Okay, that was a spiel. And so let me begin with a comment, which is actually more of a question. So I've already said something about the map pi of t. I've said that if it's not a Mobius map, that it tends to lose sets very easily. But it doesn't stop it being differentiable. So when is the map pi of t from this to itself, assuming the metrics are not isometric, when is this differentiable? And it transpires that it's differentiable quite a lot of the time. So in particular, if we assume that the metrics are not isometric, so if G0 and GT are not isometric, which means that this isn't a Mobius map, then what happens is that pi of t has a graph. It's a homeomorphism, so it should look something like that, which is like a devil's staircase. In some appropriate sense. Quotation marks always mean I'm being kind of vague. And in particular, it means that the derivative actually exists for almost all points, for almost every point with respect to the Lebesgue measure. Although the derivative at these points turns out to be 0. You can't deduce much more about the function because you don't know much about what happens at the other points. But it's a bad map, so it's behaving badly, basically. And so there's a set of 0 measure for which the derivative doesn't exist. And in fact, this set you can say even more about. So we can denote by alpha of t the points within this 0 measure set, so the points in the boundary, with the property that the derivative at that particular point doesn't exist. So the set of points for which it doesn't exist has got to be measure 0, because it's equal to 0 for almost every point. And in fact, this Hausdorff dimension turns out to be somewhere between 0 and 1. It's just another calculation. Is that good for anything? Yes, because then, finally, instead of looking at this function d of t, which is the Hausdorff dimension of some measure, you can actually look at the Hausdorff dimension of this set of points, which is between 0 and 1, for which the derivative doesn't exist. And so the corresponding result, which I'll put over here, so Kurt gets a board to himself, this one gets I. I believe not. I think generally it's either 0 or it doesn't exist. Or at least the Hausdorff dimension of a set of points for which it doesn't exist is the same as the Hausdorff dimension of a set of points which it might exist and something else. So let me modify my answer. The answer is, I think the answer is no. I think that all the points, it's either infinite or 0, but even if it's not, and I'm wrong, the extra points have 0 Hausdorff dimension to cover myself. Okay, so here is a theorem, which is due to Richard Sharp and myself. And it just says the following, that if you look now at the second derivative of alpha of t, and of course I take the derivative at 0 because that's where I'm looking at these sort of tangent vectors, so second t equals 0, then this thing is actually more or less the same as the Weil-Petersson metric squared up to some constant. The minus sign is because it's convex the wrong way, of course, and now it's minus 1/3, 1 over the area of S. So this is a analogous statement to the one over here. So this one says that you can look at the Weil-Petersson metric in terms of what the boundary map does to measures, and this simply says that you can write it in terms of the dimension of the points to which it's not differentiable. Okay, so I always stagger my talks so that I can chuck stuff away if I run too late or too slow. And according to my calculation, I have maybe 4 minutes or 5 minutes. So let me finish with a remark. Another comment I make is that when I say remark, it usually means that you can ignore it. It's just there for padding in the talks. In fact, perhaps most of the talk is like that, but we don't know. Presumably when it's within reach, I can just pull it down. So let me make a remark, which is that you can also think of this function alpha of t. If you're not a great fan of Hausdorff dimension, you can think of alpha t in a completely different way. And one is you can relate it to work of Mark Berger. And so many moons ago, Mark Berger defined for different Riemann surfaces the concept of the Manhattan curve. So it's about to make an appearance. So this is a brief remark. So this is an alternative way of thinking of this. So alpha of t can also be related to the Manhattan curve of Berger. And this, I believe, dates from 93. And for those of you who are not quite so familiar with these things, the way it works is the following. You take two numbers, A and B, which are positive. And then for these two numbers, you define the following object. You define a series, which I'll denote by, I'll put a t here to remind myself that I'm using two metrics, G0 and GT. And this thing for A and B is defined to be the infinite series where you sum over the elements of the group. And for each element of the group, we have the two different notions of length. Maybe instead of group, I should have written something else. Maybe I should write pi1 of S, like a real geometer does, maybe, which is the same as gamma. And I look at the series, which is minus A, the length of the curve with respect to the first metric, minus B, the length of the curve with respect to the t metric. And this, of course, is where t is going to be an element of minus epsilon, epsilon again. So it's a series. It depends on two parameters, A and B, and that's how it's defined. And so there's two possibilities, well, perhaps there's more. One is that it diverges, and one is that it converges. And so if you draw a picture, here's the A-axis, and here is the B-axis, then in fact, what happens is that it looks a bit like that. Not a very good picture. It cuts the axis at 1 and 1 in both parameters. Oh, I haven't said what I'm drawing. Maybe colored chalk can make an appearance. That'd be great. So this region up here is meant to be where the series diverges. So this is where eta t AB diverges. And the region under the graph, which is convex, is meant to be where it converges. And there's various things you can prove. One is that it goes through the values 1 and 1 on the two axes. It's convex, it's analytic. And I can call this curve M of A. So I'll let the Manhattan curve, which is called M of A, is the curve between where the series converges and diverges. So that's just a definition. Nothing's happened yet, which is always good. And so in particular, in this picture, well, you can see that the line between, if you draw a straight line between these 2 points, it should have slope equal to 1. And in fact, this is a nice analytic curve. So in particular, there will be, and convex, so there's going to be some point down here for which the curve also has slope equal to -1. So this is a curve here of slope equal to -1. And it will occur at some value down here. I'll call it A0. I'm now wishing I'd drawn a bigger picture. And this point up here called B0. Why not? It's got to happen somewhere. And so in particular, we choose A0, which is going to be strictly between 0 and 1, with the property that the derivative of this curve, distinguishing between divergence and convergence, at the value A0 is equal to -1. It looks better in the picture. And then we let B 0. Well, that's not very exciting. It's just the image under the curve. So B is going to be M of A0. So I've got two numbers. And then finally, you can define alpha of t to be equal to A0 plus B0. I'm now wishing I called it AT and BT, but that's life. So given any two metrics which are distinct and not isometric, this curve is convex, and so we can write down a particular function, and we can read it off this graph. And the graph is just as defined by this particular curve. And if you use this definition of alpha of t in place of the dimension one for the boundary, it leads to the same conclusion. It's exactly the same function. So the value of alpha of t is the same. It's the same function. It's a different interpretation. Alpha t can also be related to this thing. Right. No, not at all. It's a brilliant question. As I said, I'd rather wish that I put a t in here so it looks like a function of t. Maybe I can still do that. What do you think? Let me just change these to t's. Having something that doesn't depend on t differentiated with respect to t looks kind of stupid, so let me just change it. Right, so this definition here does not depend on what the boundary map does, although of course it does implicitly because you need something to be true up here. And how do you prove any of these results? You use thermodynamics, basically. You use pressure, variational principles, subshifts of finite type. You put it into some sort of pot, you stir it up, boil it for long enough, and then all of these things come out in different ways, spilling over the edges. Okay, thank you very much. I think the answer is no. The second derivatives are more or less the same, up to a factor of 4. But basically, they all, as I said before, I mean, they all come from the pressure of something and its second derivative. So they're fundamentally rather similar, but not exactly the same. Same up to second derivative, give or take a factor of 4. Well, I think it's because that André Weil and I'm not sure what Peterson's first name was. I should know these things. In their infinite wisdom, didn't know a lot about thermodynamic formalism, so they chose a normalization that they thought was more appropriate. And I think that when you do it using the dynamical approach, it just comes out differently, but it's only by some factor. So I don't think there's no great significance to why these constants occur. The reason that there's a difference between a factor of 4 in that formula and in that formula is just related to the fact that as you take t closer and closer to 0, this point at actually gets closer to a half. The thing gets a bit flatter. So that's the reason there's a 4 difference between these two formulas. It's not very deep, but that's basically it. There are very smart young people here thinking about such things. And there's also more senior guys like Le Drapier apparently also thinking about such things. I have not thought about it myself. I don't see any reason that one could not do. I mean, the proof itself, the ideas themselves, they're quite abstract. They use axiom A flow stuff. And so that works for infinite area surfaces and pairs of pants, anything you like. So theoretically, I don't see any reason you couldn't do that. And then I guess it's the same philosophy. You put it into a pot, stir it up, boil it, and something will come out. Like bouillabaisse or something. I could. It's actually, it's a consequence, let me try and think of some way to finish the sentence. It's actually not geometric, it's completely dynamical. So the reason is that in a lot of things that one does in ergodic theory and in symbolic dynamics and stuff like that, it's quite convenient to have ratios of things being equal to 1. So this value here comes out of the ergodic theory, like averages, where something is equal to 1. It happens a lot in things called multifactor analysis, which we have an expert at the back. Well, several experts in the audience, in fact. And so it's the same reason for that. So there's no geometric reason. It's just something that comes out of the dynamics. Not a very good answer, I think, but that's the best I can do, I'm afraid.